This conference will now be recorded.
All right, so this is the 4.4, 4.5 notes we were working on today in class, and I'm trying to finish up some of the ones we skipped. So we're graphing some natural log functions, and we have to remember that we started talking about this in class, but you have to keep the inside of that natural log greater than 0, so it'll be defined. So we set the inside greater than 0, and we say that we need values x greater than -1. You don't want to just start with 0 right away, even though that is bigger than -1. You want to pick something a little bit closer to it. So I picked -0.5. Then we picked a couple more values larger. So you just take your calculator and you're going to type these in. So we're going to do, I have to do mine a little backwards. So 1 minus 0.5, and then take natural log of that. So that's -0.69. Then 0 plus 1 would be natural log of 1, which is going to be 0. 1 plus 1 would be 2, so natural log of 2 is 6.69. And 2 plus 1 is 3. Natural log of 3 is 1.10. So pretty much this is the same graph we got earlier today when we graphed this one, except it's been shifted to the left. So this one has a vertical asymptote at -1, and at -0.5, we're down at -0.69, 0, 0, 1 positive 0.69, and 2 is at 1.1. So the same graph we got for natural log of x, just shifted to the left 1. Okay, so then let's look at this next one. This says we're going to take our natural log of x, which means we can pick any x's greater than 0, since that's just x, and we're going to multiply them by -2. So multiplying something by a negative should flip its graph upside down, essentially, and we're stretching it vertically, if you remember that from algebra class. So we can pick anything greater than 0. So you don't want to go too big yet, so we'll do 0.5, 1, and 2. That should be enough points. So we'd have to do 0.5 natural log, and then we times that by a -2. So that's 1.39. Then we do natural log of 1, which is 0, times by -2 would still be 0. And then natural log of 2, times that by -2, that's -1.39. So we plot this. This is, so 0.5 is at 1.39, 1 is at 0, and 2 is at -1.39. So notice this is still a logarithm graph, but it's flipped upside down. Okay, so we went over the inverse properties and the properties of logarithms. We did all of those examples. We did all of these. And then I left us just the evens on the solving part. So let's start with this first one over here, number 2. Oh, I don't know why that graph went with us. We will get rid of it. Or not. So we need to isolate the e to the x to make this solvable. So e to the 2x equals 8 over 3. To get rid of your e, you want to take the natural log of both sides, because that will allow us to bring that power to the front. So we bring the 2x to the front using one of our properties we learned today. And that just leaves us with natural log of e right there. Natural log of e is always a 1. So this is just 2x equals natural log of 8/3. Divide everything by 2. So we just need to type this into our calculator to get our decimal approximation. So 8 divided by 3, and then take natural log of that, and then divide it by 2. So I'm getting 0.49 for this one. Okay, let's look at our next one. This one, we need to isolate the e again. So we need to add that 7 over. So that'd be 17. Then divide both sides by 5. So you do this so that when you take the natural log, all you have is to worry about is the e on that side. So natural log of e to the 0.2t equals natural log of 17 over 5. We can move the 0.2t to the front. And notice I'm not even going to write the natural log of e because I already know it's 1. Just naturally is going to go away. And then we divide by 0.2. So natural log of 17 over 5 divided by 0.2. 5 natural log, and then divided by 0.2. So I'm getting 6.12. Okay, for number 6, you have a natural log already, so you're going to try to turn this one into an exponential. Remember, it has a hidden e here, so this is e to the 4th equals x when we turn it into exponential form, and that allows us to use our button for e. So that is 54.60, because the 9 will get bumped up to 10 because of the 8, and then that bumps that up as well. So that would be 54.60. And then the last one on this page, we need to isolate that 1.04 since it is our base to our exponent. So we'll divide both sides by 800, so that makes that 1.04t equals 2. Then we want to take the natural log of both sides so we can pull the t down using the power rule. Now this time you have to be careful because that's not a natural log of e, it's actually a number. So this is t times natural log of 1.04 equals natural log of 2. So you're going to be solving this by dividing. So natural log of 2 divided by natural log of 1.04. And when I did that earlier on my calculator, I got 17.67. Okay, so those are those. And then we did 9 in class, and I said I was going to do 10 on the video. So let's look through that one. It says the population P in thousands of Orlando, Florida from 1980 to 2013 can be modeled by the formula P equals 130e to the 0.0204t, where t corresponds to the year 1980. So if 1980 is t equals 0, we want to know what would we do if we wanted to go to 2013. So we need to subtract 1980 to find the number of years that have been there. That's 33 years. So this is 33 years in the future. So we're going to plug that in for our t. So this one's just plug and chug. So 130e to the 0.0204 times 33. And when I typed that in on my calculator, I got 255,865, since we're talking about whole people. Okay, then it says, in what year will the population reach 310,000? Now, when you plug it into the actual formula, notice 130 was standing for 130,000 because they told us it was in thousands. So we only need to use the 310 when we plug it in for P, because that's the thousands part. So that's 0.0204 T. We'll divide by 130 to get the E by itself. We're going to take the natural log of both sides and pull that power of t to the front with the decimal with it. So that's 0.0204 t times natural log of e. So that's going to cancel out. And so we're just dividing this by that decimal after we do the natural log. So let's type that in. So 310 natural log divided by, oh, sorry, I was supposed to do 130 in there. 310 divided by 130. And then we take the natural log and then we divide that by the 0.0204. So that is 42.5 years, or 6 years, so it's going to be about 43 years. Because it'll round up. So then we can find actually what year that is. So just go back to 1980 and add 43. Because they did ask us for the year that it happens in. So in what year? The year would be 2023. Okay, we did 11 in class, so now we're going to do 12. It says the demand function for a product is given by this following formula, where P is the price per unit in dollars and X is the number of units sold. Find the number of units sold when the price is 200. So we're plugging in 200 for P. So 200 equals 6,000. 1 minus 4 over 4 plus e to the negative 0.002x, close parentheses. I would divide by 6,000 first, so that's going to be 200 divided by 6,000 equals 1 minus 4 over 4 plus e to the negative 0.002x. So then this would reduce to 2 over 60, so that's 1 over 30. We're going to subtract this 1 over. That leaves us just this fraction on this side. So we're just trying to simplify this down so we can get the e to the x part by itself. So that would be 30 over 30. So that's going to be negative 29 over 30 equals negative 4 over 4 plus e to the negative 0.002x. You can cross multiply here. So what is 29 times 4? That'd be negative 116 plus negative 29 e to the negative 0.002x equals negative 40 times 30, or negative 4 times 30, sorry. So that's negative 120. Then we would add the 116 over. So we're just trying to isolate this e part, and it's a little harder in this one, which is why I didn't want to do it in class. So it's going to be, you're actually adding 116, but it's going to be more negative. So it's going to be negative 4 over here, negative 29 to this. So we've almost got the e to the x part isolated. So it's going to be e to the negative 0.002x equals 4 over 29. And then we finally can take a natural log of both sides. It ends up being natural log of e times just this guy, negative 0.002x equals natural log of 4 over 29. I skipped the part where I brought the power to the front because we kind of get that pattern every time. So if we divide, this is just a 1, so if we divide by that negative 0.002, we get, and I already did this earlier, I think it's 991 units. So it's quite a lot. Now that one's much harder than anything on the test. It's more like a homework question. Okay, so let's look at the 2 that I skipped on the derivative of the natural log. Remember, the rule is if you're taking the derivative of natural log of x or natural log of any function, essentially, you always write 1 over the original inside of the log, so that's 1 over u, and then you chain the derivative of u. So this means u prime right here. So for this guy, you might want to rewrite it as x plus 1 to the 1/3. So this is going to be, the derivative is 1 over x plus 1 to the 1/3 times the derivative of this, which would be 1/3 x plus 1 to the negative 2/3, because we'd have to subtract a power. And the derivative of that chain inside is just a 1, so we're okay there. So this is 1 over 3. And then this moves down to the bottom, so I have an x plus 1 to the 1/3 plus 2/3, so that's just 1. So this guy actually works out to a really nice, clean derivative. I'm just going to write it a little bit prettier. So it's 1 over 3 times x plus 1, because you have these 2 guys that move down to join the 1 that's already there. Okay, so for this one, it's a little bit more complicated because it's a product rule. So the first step is to write it as 1 over itself. So x squared, square root of x minus 1. Then we have to take the derivative of that and chain that along. So let's do our product rule there. So x squared and 2x, x minus 1 to the 1/2 is 1/2 x minus 1 to the negative 1/2. So when we cross multiply that, so I'm doing my work up here, 2x on the square root of x minus 1 plus, that would be x squared over, and these are both going to the bottom, so 2 square root of x minus 1. This is not a quotient rule, it's a product rule, so we don't need a denominator here. We just need to get a common denominator for this. So if you times this by another x squared, square root of x minus 1 on top and bottom, that would leave you with a 2x, x minus 1 on top, plus x squared, all over a 2. Oh, we need a 2 up here as well, sorry. It's going to be a 4, because this guy has a 2 in his denominator. So over 2 square root of x minus 1. So I'm kind of running out of room there. That's 4x squared minus 4x plus x squared over 2 square root of x minus 1. That's 5x squared minus 4x over 2 square root of x minus 1. Okay, so I'm going to chain that along to this. So I have 5x squared minus 4x over 2 times square root of x minus 1. So y prime is, I can pull out an x on top. that I'll cancel with one of those x's on bottom. So that's 5x minus 4. I have that 2x squared, and square root of x and square root of x is just x minus 1. So that will cancel one of the x's on top with bottom. So my final y prime here is actually really not that bad looking. It's 5x minus 4 over a 2x times x minus 1. Now this one is way too hard for anything on the exam. It's just kind of showing you how all of the pieces of things we've learned are kind of tied together. So we did both equations of the tangent lines in class, so that leaves us with these 3 word problem areas before we get to the next slide. So these are just applications of the stuff we've been learning. So this says find all the relative extrema of this function. Consider the domain. That means that you can't, because remember this is a natural log here, you have to have x is greater than 0. So if we get critical values that are below 0, we can't use them when we talk about max and min because they don't exist in the function. So the derivative of this guy would be 4x minus 1 over x for the derivative of natural log. Get a common denominator here, that'd be 4x squared over x minus 1 over x. So 4x squared minus 1 over x. So if we set that equal to 0, that would be, this is a 2x plus 1 and a 2x minus 1 over an x. So the top equals 0 when we either have negative 1/2 or 1/2. The bottom equals 0 when we're 0. But because of our domain, we can't consider this one or this one. So it only can be the 1/2. That's the only one that actually exists in the function. So if we plug in 1/2 into the first derivative, well, actually not 1/2, the test values on each side. So, and they have to be test values that are in our domain. So point maybe 2 and 0.8. So if I plug those into here, because this is my first derivative, I could actually make my life easier and just pick 1 for the one on the other side. But we had to pick a decimal between 0 and 0.5 for this one. So if we plug in, let's do 1 first. That'd be 4 minus 1 is 3 over 1. So that's coming out positive. If you do 0.2, 0.2 squared times 4 minus 1, and then divided by 0.2. So notice that comes out negative. So this goes from decreasing to increasing, which means this is a relative min. So we have a relative min at just x equals 1/2. And I don't care about the actual ordered pair right now, just making sure we consider the correct values. Okay, so this says a group of 200 students was tested every 6 months over a 4-year period. The group took the Spanish test their first semester of college and then did not take any more Spanish classes. The average test score, P in percents, is modeled by P equals 92.3 minus 16.9 natural log of T plus 1 for T's between 0 and 48. So otherwise, if it's been more than 4 years, then this formula doesn't work anymore. So it says, yeah, so at what rate is the average score changing after 1 year? Now notice, we did a problem just like this a minute ago, and we just plugged and chugged in and solved. That is not what we are doing here because they said at what rate was the average score changing. That means we need dp dt. So dp dt is the derivative of this. Now 92.3 would have no derivative, but this guy does. That is negative 16.9 times the derivative of the natural log. So that's 1 over t plus 1, and then you chain the derivative of the bottom, which is just a 1. So it looks like we're plugging into negative 16.9 over t plus 1. Now it says, at what rate is the average score changing after 1 year? So we're plugging in 1 for t. So negative 16.9 over 1 plus 1 is negative 16.9 divided by 2. Oh, that's 1 year. Sorry, I'm not paying attention. We are not plugging in 1. It's 1 year, and this formula is in months. Pay attention to your reading. I'm talking to myself. So this is 12 months. Sorry, we are plugging in 12. So t plus 1, and we're plugging in 12 months. So 12 plus 1 is 13. And that reduces down to a negative 1.3%. So after 1 year, they every time you move another month forward, they're going to from that point at that specific point. So if you go to month 13, then they're going to lose another 1.3% of the knowledge. Okay, and then we did not do 11 either, so let's look through that one. It says the cost of producing X units of a product is modeled by this cost function when, and notice they've given us a domain that makes sense for natural log, except they didn't let us go down to the decimals between 0 and 1. So it says find the average cost function. So remember, average cost function just means you divide everything by X. So C bar is 500 divided by X plus 300X divided by X would just be 300 minus 300 times the natural log of X divided by X. So I'm just kind of grouping that together. So that is the average cost function. Now, find the minimum average cost. That means we're looking for max or mins, which means derivative. So we need to take the derivative of this with respect to the X. So if I do that, that would be, this is 500 X to the negative 1. So that's going to be negative 500 over X squared plus nothing for this guy because that's derivative. That would be 0. Then we have a minus 300, and we need to do the quotient rule right here. So that would be natural log of X and its derivative, bottom and its derivative. So this is 1 over X times X minus natural log of X times 1 all over the bottom 1 squared. So that is 1 minus natural log of X all over X squared. We did that guy earlier. Okay, and that's going to be times the 300, so we're going to distribute that. So negative 500 X squared minus 300. I'm going to go ahead, since they have the same denominator, we can make this one fraction. They are both over X squared. So this is negative 500 minus 300 plus 300 natural log of X, because that one gets distributed to that as well, over X squared. So that is negative 800 plus 300 natural log of X all over X. The bottom equals 0 when you're at 0, but that's not in our domain, so we can't consider that for a critical value, and it's undefined. So we have to look at just when is the top equal to 0. So negative 800 plus 300 natural log of X equals 0. That's 300 natural log of X equals 800, or natural log of X equals 8 over 3 if you divide them. So this is e to the 8/3 equals X. So we need to work that out. And I got 14.39 for the answer to that part. Now, that may not be what we're actually looking for because X stood for the units. So it was X units. They asked us to find the minimum average cost. So once you have your units that produces a minimum, you have to plug it back into the function to find the actual cost. So if I plug that in, that is C bar equals 500 divided by 14.39 plus 300 minus 300 natural log of 14.39 divided by 14.39. So you have to plug it into this function. And when I did that, I got 279.15 per unit. So that's the average minimum cost. Okay, so that gets us to the very last page. I skipped over some of these just because they're not that bad. This says evaluate the logarithm without a calculator. The way you do that is you imagine if it was set equal to your exponent, which is your x, the thing you don't know, and you just use the spiral to solve these. So this says 2 to what power equals 16. So that would be x equals 4. This says 10 to what power equals 100. So that would be that x needed to be squared. This is 10 or 3 to what power equals 1 over 81. Now 81 is 3 to the 4th, but because it moved to the denominator, that means our x was negative 4. And then these are the change of base problems. So if you want to use your calculator to evaluate something that's not base 10 or not base e, you can change them to either natural log on both top and bottom or log base 10 on top and bottom because your calculator has both buttons. but is always so we're going to use the one they gave us here, the natural log. It is always the big argument number as the top natural log, and the bottom base number is the bottom natural log. So if you just write each of these in that format, then we can use our calculator to evaluate them. And when I did that, I got 2.32, and then 3.16, and then negative 0.86, just using my calculator and the buttons. All right, and that leaves us with just one last example. And that is, can we take a derivative of x times 2 to the x, which is a product rule. So my first function is x, its derivative is 1. My second function is 2x, its derivative is using this formula. So it's natural log of 2 and times the 2 to the x. So if I do my product rule, this would be 2 to the x times 1 plus 2 to the x times natural log of 2. It doesn't matter which order you write that in. Because I like to notice that things that are alike are in the problem, I take that out usually. So that's 2 to the x, and that would leave me with 1 plus natural log of 2 times x, if you want to write it that way. Because then we could solve this piece right here for x. So that is everything for this unit. So I'm going to post this video, and on Tuesday we will take questions on your worksheets, and we'll also talk about the exam. Have a good weekend, everybody.